in terms of, so tomorrow we'll use the model of the two shells to study transfer reactions. That, of course, is not so close to reality, and so we thought that maybe one could, as a little project, generalize that into a model that Pete discussed in terms of generalized seniority. So anybody who's interested in that, let me know, and we can chat. And I talked to a few of you maybe are interested to do something on pairing. I'm somehow feeling inadequate perhaps to do that, but just let me know if there's still some last minute interest there. I thought I was going to give a lecture today, but it turns out that it's Rick Kasten's turn, so I'll give you a little short discussion of the two problems that we discussed yesterday, and then tomorrow we recap at the beginning of the lectures with, oops, I'm being attacked by bees. Tomorrow we'll recap a little bit the activities. This is the problem number one, which was related to this sort of back of the envelope estimate of whether we would expect, from what we know about the nuclear force in very simple terms, whether the transition may happen between the spherical system driven by the pairing correlation or the one driven by the quadrupole term. And we saw yesterday you have the mean field. You can have that as you remember as an average, if you like, of the two body interaction. And then we discussed by the work of Molinari Schiffer that the first two terms, the most important ones, are the quadrupole and the pairing. You can then yourself assume that if you have a number of levels here, each which is assumed to have an order of omega degeneracy, then the distance between the levels here is about A over omega, and then the distance, you compare that with this will be from there, V0 over A over omega. This translates to that, and then the question is how this is compared to G omega. This is 2 divided by the parameter x, which is here, and Rick will use it later, which is this so-called control parameter that drives the transition from pairing to normal system, and then it's easy to show that this ratio G over V2 is about that. Because we know that x has to be less than 1, because otherwise there would not be any shell closed shell nucleus, then this means that G over V2 has to be less than 1. And this was the condition that we derived for the transition to the quadrupole. This, of course, again, I'm trying to tell you, this is just a back of the envelope that allows you to understand this basic feature of nuclei. If you have to do a specific case, you need to do that in a more realistic approach, but this is very robust. And it's also robust, this other problem, which was, yes? Well, because if you remember, the way we wrote the mean field was an average of all the two-body interaction. So if we assume that the average is equal for everybody, then you have an average of that two-body, And the average, because of Schiffer and True and Molinari, we know that this term is mainly a delta function plus a P2. This one has a G here, this one has a B2. So those are the strength of those parts. So the mean field is made out of the average. There is no mean field per se in the nucleus. It's made out of the average of the two-body interaction. The Hamiltonian, as you recall, is a kinetic energy term and a two-body term. There is nothing else. Well, three-body, of course. So what you do is you rewrite this in terms of a mean field and a residual interaction, which is the difference between the total two-body minus the average. We can go back to that. So this was the starting point, the kinetic energy of each single particle, each of the particles, and then they interact by a two-body force. And then you rewrite this term as this mean field, and that's the mean field that I'm talking about. That one, as you can see, comes from an average of this one. This U here is that. It's an average of those two interactions of the two body. There is no such a thing as, I mean, you can cast that as a mean field, and the depth of that mean field comes from summing all the two body interactions. Yeah, and then we argue later that by looking at the residual interaction, you convince yourself that the two main ingredients are pairing and quadruple, and then you say the mean field, then of course that's an approximation because there are other terms, as I said, and then the depth of the potential B0 has to come from an average of those other two body interactions, which are pairing and quadruple. And then you, from that and the other things that you know, then you can conclude that B2 has to be less, no, sorry, G has to be less than B2. Now, you can also do it in a different way, because I told you roughly what Schiffer and True and Molinari determined for those parameters. If you recall, Schiffer and True found that G was 20 MeV over A, and B2 something of the order of 30 to 40 MeV. And the second problem, which is even simpler, was show that indeed in nuclei this control parameter comes to be very close to 1 or less, or in the neighborhood. So the nucleus is already very close to instability of the pairing phase transition, because omega, that's something that you have to actually determine with the harmonic oscillator. So you have that harmonic oscillator levels that I gave you, and you can estimate roughly that omega should scale like A to the 2/3. The bigger the system it is, the more degeneracy is. And then G already know, 20 over A, and then D, we take that as roughly the H omega 0 of the harmonic oscillator. When you plug all this in, you get that X apparently is close to 1, as we know. So for lead 208, for example, closed shell nucleus should be less than 1 because they are closed shells, As you move out, like in the teens we discussed yesterday, the x is a little bit bigger than 1, making the transition to the pair system. So I guess unless there is another burning questions, we'll recap tomorrow, and I'll be around today if there is any other questions during the activities in the afternoon that I can discuss with you. Also, as I said, any interesting on the project. So thank you, Rick.
I thought for a minute you were going to lecture tomorrow.
Maybe not tomorrow, huh?
No, that's fine.
That's you. This is you. And I get out of the way.
Okay. I just want to make a couple of quick comments before I start what I'm going to talk about today, which is the Nielsen model. You've been hearing topics, you've been hearing many speakers talking about seemingly different topics, but there are a lot of themes that run through them that are common. And since you've had so much thrown at you in a couple of weeks, it may not always be obvious. So I just wanted to make a couple of comments relating some things that Gusto talked about yesterday to things that I talked earlier. So you see that we're really very often using the same ideas, talking about the same things in different words. Augusto talked about this X parameter. Let me get rid of his field, which is X equals 2G omega over D. This is the interaction, and that's the spacing between the levels. And that is, I won't blow this up, I think you can see it. That is, remember we did two-state mixing in the first day? That's essentially, that's 1 over my R parameter. My R parameter was the unperturbed spacing divided by the interaction. And so everything I did there with these plots, you can translate directly to what he did. Okay. Secondly, he talked about V pair going as number of nucleons and the residual going as the number of nucleons squared. And if you remember, we talked about the P factor, which is number of valence protons, number of valence neutrons over the sum, as a measure of the competition between pairing and proton-neutron interaction. It's exactly the same idea. This goes as n squared, this goes as n, and so that's exactly the same competition. So when I saw him write this, I immediately thought, okay, it's the same physics. And one other thing is he talked about, and I want to make sure I get this right, Augusto, you talked about the Fermi surface as a function of nucleon number having a kind of staircase behavior in the absence of pairing, right? And then pairing smooths it out?
Correct.
Okay, and
That's one of the main features of the pairing.
and we talked about something very similar. Remember those two guys going off there? When we talked about two nucleon separation energies. And here you see throughout most of a shell these linear behaviors. You would think as you fill neutrons that you would fill neutrons at a certain separation energy, and then when you start filling the next orbit, the separation energy would drop. The next orbit, it would drop more, and you'd have something that would go like this, like a staircase, but in fact, it's smoothed out by the interactions. Now, the fact that it's not smoothed out at closed shells shows you a point which Augusto made yesterday, that pairing doesn't totally dominate. It's really a competition, And when you have a big gap between single particle levels, you really see it. Okay, those are just a couple of comments relating.
In that plot, during the smooth part, x happens to be larger than 1, and near the closure, x becomes less than 1.
Okay, all right, okay. So let me get rid of that. Okay, today I want to talk about the Nielsen model. And the Nielsen model is the model we go to first and quite extensively to understand the behavior of deformed odd mass nuclei. So you can think of it as a deformed independent particle model. And the way we use it, in fact, is even simpler than for spherical nuclei. We use the independent particle model plus residual interactions. The Nielsen model, in a sense, is used in an even simpler way. So I want to describe that and discuss some aspects of it, including Coriolis mixing. And so since in heavy nuclei, most heavy nuclei are deformed because the shells are big, there are lots of valence nucleons. Recall again the p factor. If NP and NN can get large, this will always be greater than 5, which is kind of the boundary between spherical and deformed. So in heavy nuclei, you always get these regions of deformation. And so it's pretty important to have some model, some independent particle model for non-spherical nuclei. And that's what the Nielsen model is. So just to start the discussion, we're going to limit ourselves to nuclei that are axially symmetric or nearly so. The vast majority of nuclei of deformed nuclei are very close to axially symmetric. You remember this parameter gamma, which can range from, in one convention, 0 degrees for a prolate deformed nucleus to 30 degrees for axially asymmetric, maximum asymmetry to 60 degrees for oblate. In most deformed nuclei, gamma is between 0 and about 12 or 13 degrees. But the change in structure as a function of gamma is highly nonlinear. So that most of the change in structure of a nucleus as a function of gamma happens between 20 and 30 degrees. So for nuclei where gamma is 0 degrees, 5 degrees, 10, 12, even 13 or 14 degrees, they behave very, very similarly to axially symmetric nuclei. So I'm going to make that assumption. It simplifies things. So the question is, so here you have a nucleus with a symmetry axis Z. It can rotate around this axis, okay? And notice that's perpendicular to Z. That will come in a moment. And the question is, what are the, oh, let me get rid of the lights. Now comes something very dangerous. I've got to get to the light screen. Okay, now I know what to do. Okay, so the question is, what are the energies of particles in orbits in such a nucleus? What are their wave functions? They somehow will have to be different than in spherical nuclei. What new features enter, and what about residual interactions? Those are the questions we want to kind of address. And it's sometimes useful to give physics a personal aspect. So I was thinking of this coordinate scheme, and I was thinking of something we saw on the tour. And there is Navin simulating a coordinate scheme. Whoops. So there he is. This is the z-axis. He's going to rotate about this axis. Anyway, so now you understand coordinate schemes. Okay, so here's the answer to the question. This is the answer to the question of what are the energies of orbits of particles in an odd mass deformed nucleus. Okay, now, how many of you have seen this diagram? Most of you. How many think it's complicated? Okay. How many would like to find out that it's very simple? Okay, good. Some of you don't seem to care. Okay, so I'm going to try to explain this diagram and a couple of features to notice. So what the diagram shows is this is deformation here. And instead of beta, I use something called epsilon. I'll comment on that in a minute. This is epsilon equals 0. That's a spherical nucleus. So these energy levels here are nothing more than the independent particle model levels. And here you have the standard magic numbers, 82, 126. Here you have, I'm sure you know all the orbits in each shell by heart by now, but here's F7 halves, H9 halves, I13 halves, P3 halves, F5 halves, P a half. Okay, and what you see is that as you turn on the deformation, as the nucleus goes from spherical to something shaped like a prolate American-shaped football, each of these levels, which can contain 2J plus 1 particles, there's degeneracy breaking. So this is F7 halves. I know you can't read it back there. F7 halves can contain 8 particles. And in the independent particle model, all those particles would be at the same energy. As you turn on deformation, something happens, something changes. And you get 4 levels out of this F7 halves, and we'll see what they are. And so the energies change. And so the Nielsen diagram is just simply nothing more than the independent particle model shown for every possible deformation. Okay? If I picked a deformation at point 3 and showed these levels, that would be the equivalent of showing the independent particle model for 0 deformation. It's just convenient to show everything all at once. Okay. So we want to understand this. We're going to do it in 2 ways. A formal derivation, which I'm going to go through very quickly later on because it's in every textbook and there's nothing I can say that you can't see in the textbooks. But first I want to derive it without any calculation whatsoever. This is a slight lie. You have to be able to calculate a cosine, but that's all. Okay, so first of all, a comment about deformation variables. We've talked a lot in this course about beta. You just saw epsilon on that diagram. There's also a thing called delta. And by that, I don't mean, well, I'll say this first. This delta, to all intents and purposes, these are about equal. They're all within 5% of each other. So for the purposes of this course and almost everything you'll ever do, you can treat them as equal. They arose for different reasons, which I won't go into unless someone really insists, but you can treat them as more or less equal. There's an older parameter which I haven't seen in years, which is called eta, and that's about 20 times beta. And I just write that there in case you ever see it. But beta, epsilon, and delta are effectively interchangeable. Okay, so for a nucleus, we have 2 shape parameters, beta and gamma. We're going to ignore gamma today. And so beta is the quadrupole deformation. And you have the 3 Euler angles, which tell you the orientation of this nucleus in space. As I said, we're going to assume that the nucleus is actually symmetric. Okay, so the Nielsen model. Here's the shell model, or independent particle model. And if I pick some random deformation, I would have some levels. And that would be the Nielsen predictions for that deformation. But, as I said, it's convenient to plot all the deformations on one single diagram. And so you have these diagrams. So I show 2 of them here. One is for the shell from 50 to 82, and the other is for the shell 80 to 126. And the main thing I want you to see here is the similarity. In each shell, you have a bunch of orbits going down, some orbits going flat. Their energies don't depend on deformation much. Some orbits going up. And then you have some orbits from the next shell coming down, and some orbits from the previous shell coming up. And you have the same thing here, a bunch of orbits from the shell we're talking about, and then some sometimes called intruder orbits from the next shell, or extruder orbits from the lower shell. Okay? So since these diagrams are very similar, if we can understand any one of them, we can effectively understand all of them. So I'm going to use this one mostly, almost solely. And so let's look at that again. And then I want to simplify it even further. Here's the 82 to 126 shell. We know that the 50 to 82 shell is similar in behavior And these are just the last orbits from that shell that are rising up. They're sort of equivalent to these orbits which are rising up. These orbits from the shell above 126 that are coming down are functionally equivalent to these ones coming down. So all we have to do really is understand this group of levels. And if we can understand that group of levels, then we're in pretty good shape. So what I'm going to try to do is explain that, and I just isolate it here. So this is just a blow up of this section here. So this is what we need to understand. We need to understand why these split, and if you look carefully, you'll notice some of them curve. And we need to understand why they curve. Each of these levels, or orbits as they're usually called, has some numbers attached to them. And you saw this in Augusto's lecture yesterday, and you didn't explain these quantum numbers, right? I don't remember you explaining them. I will explain them and tell you what they are. They look complicated, but they're actually very simple. And they help you understand what the nucleons are doing. Speaking of nucleons, last night we went into town to a restaurant. We passed a restaurant called the Nucleon. Yeah? Is that good? Is it related to Ganil? No. No to both of them? No. Okay. It was sort of appealing. Okay, so what do we need to understand the Nielsen diagram? We need two ingredients. What do you think they are? What about the nuclear force? How about short range? Okay. Sorry? So what we need is that the nuclear force is short range and attractive, and we need two-state mixing. Okay, these two ingredients are all we need to understand the Nielsen diagram. And when I say all we need, I mean just that statement, nothing more. We don't need to calculate anything. We just need to know this statement, and we need to know a little about two-state mixing. All right? Okay, so here's the Nielsen model. Here's a deformed nucleus. It's non-spherical, so it can rotate. The Nielsen model is a model that is solved in the body fixed frame of the nucleus. That is, it describes what happens inside this nucleus. But the nucleus exists in space, so it can also rotate. And the reason we can separate that is because, or at least approximately separate it, is because the frequencies of orbits and the frequency of rotation of the nucleus are very, very different. So even if the nucleus is rotating, during an orbit of a particle, you can treat the nucleus as approximately stationary. Okay, and so we can separate those degrees of freedom. Note one interesting thing so if the nucleus is rotating this way, and one particle is going around this way, and another is going around the opposite way, if it's rotating slowly, it doesn't matter. These two particles basically see the same thing. If the nucleus is rotating very, very rapidly, then there's a little bit of a difference between what this particle experiences and what one in the same orbit going the opposite way experiences. And that effect shows up at higher angular momentum states and is known as signature splitting. We won't discuss it, but just remember that if you're studying higher spin states, that can be an effect that you need to worry about. Okay, so I want to define a coordinate system. So here again is our nucleus. Here is the z parameter, the z-axis, the axis of symmetry. Everything is symmetric around that. And here is the orbit of a particle. So imagine I have a particle going around the nucleus in this direction. So its angular momentum, little j, points in this direction, perpendicular to the orbit. And there are two quantities associated with that angular momentum vector. One is the angle relative to this axis, theta, and the other is the projection of that angular momentum on the z-axis. Okay? And if you remember when I discussed even nuclei on last Tuesday, not yesterday, anyways, a number of Tuesdays ago, I used the quantum number k in talking about beta and gamma vibrations. If you remember, there was a thing called the gamma vibration, which had k equals 2, and a sequence of rotational levels 2, 3, 4, and so on. This is the wrong quantum number to use here, but I'll tell you why I'm going to use it. Properly speaking, the projection of the single particle angular momentum on the z-axis is called omega. Okay? And the reason is that k is the projection of the total angular momentum on the z-axis, the total angular momentum consisting of the particle angular momentum plus any rotational angular momentum. But in an axially symmetric nucleus, the rotational angular momentum is always perpendicular to the z-axis, so it has no projection on the z-axis, so k and omega are similar. And so I properly should be using omega as a quantum number, but I will use k, and I think most people probably use k. It's really carelessness, but it's become very ingrained in the way we think about things. Okay, it's also good to get away from omega sometimes because, you know, there are more concepts in physics than there are letters in the alphabet. And so very often we have to use the same letter to mean different things. And yesterday, Augusto used omega to mean the degeneracy of the shell. And here, for an odd particle going around the nucleus, it means the projection of the angular momentum. And so, okay, it can get confusing. Anyway, so I'm going to use k for that projection. Okay, and notice that sine of theta is k over j. Okay, all right? I said a few minutes ago the only thing you had to be able to calculate was cosine of theta. Well, sine of theta, actually, I meant. Okay, so this is the coordinate system. Whoops, whoa. This is the coordinate system. Oh, there's my comment about omega. I forgot that I had written it here. So we will use k instead of omega. Here's the coordinate system we're going to deal with. And so all we have to do is think about this and what the energies are of particles going in different orbits with different k values will be. Okay, so the question is, if you have shell model energies for a spherical nucleus, and now you deform the nucleus, let's consider two orbits called 1 and 2. I could have called them 16 and 17 or whatever, but I chose 1 and 2. Okay, so this orbit goes around the equator, and this goes what I call polar. And the key thing to notice is that the orbit 1 is closer on average to the bulk of the nucleus. The nucleus is deformed in this direction than orbit 2. And since the nuclear force is attractive in short range, that means that the particle in orbit 1 will feel a stronger attractive nuclear force than the particle in orbit 2. And therefore, its energy will be lower. Is that clear to everybody? All right, it's pretty simple, and that's the Nielsen model right there. You've got 90% of it already. So let's just look at what these signs of theta. I want to just calculate k sine of theta, basically k over j, for different values of k. So I'm going to take a particle in an I13 halves orbit, and an I13 halves orbit will have projection quantum numbers 1 half, 3 halves, 5 halves, 7 halves, 9 halves, 11 halves, and 13 halves. And so here's a table where I have those k values from 1 half to 13 halves, the angle theta corresponding to those k's. So that angle theta is just related to having, if the angular momentum goes this way, if k equals 13 halves, you'll have 1 theta. If it goes like this, you'll have a different theta. And then down here I have, and that's just calculated from sine of theta is k over j. And down here I have the differences between adjacent angles. And what you see is that for k equals a half, that corresponds to an angular momentum going like this, and k equals 3 halves, which is an angular momentum at a slightly larger angle, and so on. The changes in angles for low k are very small, and the changes in angles for higher k are greater. Okay, so if you take that information and go back to here, you would expect that the energies of particles in low k states would be more similar to each other than energies of particles in adjacent high k states, simply because for the high k states, the angle changes more as you go from one k to the next. Okay, clear? Okay, so let's take the I-13 halves, and this is what we would predict from this argument. So this axis here is deformation. I didn't write it, but it's deformation. Here's the I-13 halves single particle shell model, independent particle model orbit. And as you deform the nucleus, the orbit with k equals a half, let me go back for a second. K equals a half is an orbit where this angular momentum vector is pointing nearly vertically, so it has a small projection on the z-axis. That corresponds to a particle going in an equatorial orbit, so it's close to the nucleus. And the more deformed the nucleus is, the closer it is. And therefore, the more deformed the nucleus, the lower the energy of this k equals a half orbit. Okay? For a spherical nucleus, all these energies are equal. As you deform the nucleus, the k equals a half, the equatorial orbit, will go down, down, down in energy. K equals 13 halves, which is an orbit going in this direction with its angular momentum pointing this way, will go higher in energy as the nucleus deforms because the nucleus will squeeze in this direction. And so that goes up. And the spacings between these orbits will not be uniform, okay, because the change in angle of the orbit from 1/2 to 3/2 is less than the change from 9/2 to 11/2. Okay? Now, what you're seeing here, the general phenomenon is degeneracy breaking. In the independent particle model, you can put 14 particles, 2j plus 1, in this orbit. In the Nielsen model, the energies of the particles depend on this particular angle of the orbit. Okay? And you can put 2 particles in each of these orbits. The reason you can put 2 is you can have one going around the nucleus this way and the other going around the nucleus this way. And if you make the approximation that the nucleus isn't rotating while the particle does that orbit, there's nothing that distinguishes these two. They have the same energy. As I said, if the nucleus is rotating very fast, that breaks down, but we won't take that case now. So you can put 2 particles in each of these orbits. The orbits are k equals 1/2, 3/2, 5/2, 7/2, 9/2, 11/2, 13/2. That's 7 orbits. 1, 2, 3, 4, 5, 6, 7. 7 times 2 is 14. That's the same number of particles you can put in the parent orbit. Okay? Okay. So imposed on a Nielsen diagram then, what you've just seen is this effect. The I-13 halves orbit splits into 7 individual orbits, highlighted in red here. This orbit coming down here will have k as a half. This one, k equals 3/2, 5/2. Notice these are very close together. Spacing increases a little. 7/2, 9/2, 11/2, 13/2. Okay? And most of understanding the Nielsen diagram is just applying the same idea to each of these other single particle energies, orbits. So F7/2 has projection quantum numbers k equals 1/2, 3/2, 5/2, and 7/2. And so it'll break up into 4 Nielsen orbits, as they're called. This will be the k equals 1/2, k equals 3/2, k equals 5/2, k equals 7/2. This is H9/2. It'll break up into 1/2, 3/2, 5/2, 7/2, 9/2. We've already talked about this. The P3/2 will break up into k equals 1/2 and 3/2. F5/2 into 1/2, 3/2, 5/2. And the P1/2 will just have a single one. Yes?
Sorry, maybe I missed something, but is there any simple way to explain why the evolution of one shell is sometimes linear with the deformation and sometimes is not?
You mean why do some of these curve?
No, but I mean, some curve like really have a linear trend and some other do not.
Yeah, there is a way, and that's exactly the next thing I'm getting to. In fact, I think when I click this, there's going to be some text over here which says, okay, we've got it all, but what about the curvature? Okay? Yes?
So can we just go back to that first picture of the 2 different ways the circles can go around the nucleus and how this explains,
There?
you passed it. The way that you said, once you understand this, you have the Nielsen model. Yeah, this. Yeah,
That,
right here.
okay.
So from our 2-dimensional cross-section, I'm imagining this red circle is prolate,
Yes?
and in which case I can see what's happening, but what if this cross-section I don't know. Are the arguments all the exact same for oblate?
Yeah, we'll talk about that. Yeah. Well, they're the same but upside down.
Okay.
Okay? If you have an oblate nucleus, a disk, suppose this were, well, let's see. Do we have a disk? I don't want to drop that. I'll use the book. Do you know what page this is? Is that
Absolutely.
okay? So here's an oblate nucleus blown up. Okay, and if I have a particle going around this way, okay, or this way, okay, the energy will be very different in the two cases. All right, and we will talk about that in a minute. So you can use exactly the same argument. Okay, but clearly the k equals 13 halves instead of the 1/2 will be the lowest.
So our definition of Z with the prolate.
Yeah, okay. I should be careful the way I say that, but we'll talk about that. Yes.
Okay, so you're going to talk about why do we have some linear generation of the music
Yeah.
kilograms and later in things. But I think there is one of the D5 now, which first starts to go lower in energy and then starts going higher in energy.
Yeah, that. So I think
Are you going to talk about this?
I think you were thinking about this one
No, down, absolutely down.
down here.
Yes, you see, it first goes down
Yeah.
and then goes up.
Okay, that's analogous to this.
Yeah.
Okay, and yes, I will talk about why that happens. Okay, and actually, you can imagine that the wave functions of these particles depend on the deformation, and just by thinking about it, you'll actually be able to deduce the wave functions, and you'll see that this wave function of this particle has different features than the ones that are straight. Okay, so these two questions are linked, and we'll come to those in a minute. Okay? All right, so this is the essence of the Nielsen model. You just repeat this idea, I've said this already, for each J orbit, and you see these patterns. Now there's one thing that's missing, as you pointed out in your question. Some of the lines are curved. What does that mean? Where does that come from? Anybody have an idea where that could come from?
Fancy calculations.
Sorry?
Fancy calculations.
No, very simple calculations. I'm sorry? So I'll give you a hint. There were two ingredients we needed, that the nuclear force was short range and attractive, and two-state mixing. So we've discussed what happens because the nuclear force is short range and attractive. Can anyone guess where the curvature comes from? Okay, it's two-state mixing, and we'll see that in a moment. Okay? So we need to understand this curvature. It's just an example of the curvature. Okay, so you see these lines are curved, some of them. And some are straight, by the way. Notice, before I leave this, notice that all of them start off straight. Maybe only for a little while, but they all start off straight. Okay. So, what we've talked about so far is the energies in a field of a certain shape. That's a diagonal effect. But the interaction that generates the Nielsen model also mixes the wave functions of these different single particle states. Okay, and the mixing will depend on their energy separation, which changes with deformation, and it also depends on which orbits they are. Only states of the same K can mix. Okay, now later we'll generalize that, but for this pure, simple Nielsen model, only states of the same K can mix. Okay, so now remember our discussion of two-state mixing earlier in the course. And I want to look at how two states mix as a function of their energy separation. So, if you remember, if I take two states that mix, they push each other like this, okay? And if they were further, I'll call that further apart. If they're closer together, for the same interaction, they will push each other more. Okay? Remember that? Okay, so now, suppose that I take a case where the unperturbed separations change as a function of deformation. Okay, so here's the deformation axis, here's the deformation axis, and I'm taking two spherical single particle levels whose initial linear behavior starts off so that they're approaching each other. So what's going to happen due to the mixing? Well, here, this orbit will be pushed down a little, and this will be pushed up a little when they mix. Here, it'll be a bigger effect, and here it'll be a bigger effect. And so the net effect is that they will curve. Okay? And that's what I'm trying to show here. If you have two orbits, two unperturbed, remember I always used phi's for unperturbed and psi's for perturbed. If they're approaching each other and they mix, they can never cross, because remember the closest two levels that mix can ever be is twice the matrix element. Remember the degenerate case? Okay, so they can never cross, and so what will happen is they will, that's called the the avoided crossing, or no crossing theorem. And so what will happen is instead, at the point where they would have crossed, they reflect and kind of bounce off each other and go like that. All right? Now, if you remember, we had a table in the two-state mixing calculation of the mixing amplitudes as a function of the separation and the interaction. So this wave function here starts off very pure. It's just phi 2, and this starts off very pure phi 1. As the unperturbed energies approach each other, the wave functions will become a mixture of phi 1 and phi 2. At this point, they will be totally mixed. So the wave functions will be this total mixture. On the other side, this wave function will actually look more like that one, even though it started off here and you can draw this continuously. And this wave function will look more like that one. Okay? So these levels will approach each other and curve away, and that's the origin of the curvature in the Nielsen diagram. Okay? And at the inflection point, the separation has to be twice the interaction. And on the right, psi 1, the wave function is predominantly, oh my God, oh no, I said it right. It's predominantly phi 2, and psi 2 is predominantly phi 1. Is this clear? No? Yes?
So you mix wave functions, or you mix levels which only have same k. So for example,
You only mix the same k.
So for example, that would be D5 half or F5 half.
No. Those are the, let me go back to find the Nielsen diagram. Okay. So k, so for a given orbit, like F7 halves, you have 4 orbits from it. K equals 1 half, 3 halves, 5 halves, and 7 halves. From H9 halves, you have k equals 1 half, 3 halves, 5 halves, 7 halves, 9 halves. So the orbits that will mix will be k equals 1 half from this orbit and k equals 1 half from this orbit.
Yes.
K equals 3 halves and 3 halves. K equals 5 halves and 5 halves, and so on.
In the end, what, okay, when they mix very strongly and become like totally mixed, what would be the angular momentum of this level?
It'll be a mixture of the two J's.
And is that a good quantum number?
No. Hee hee. I was hoping someone would ask that. Yeah, so what happens with angular momentum is not conserved? Uh-oh.
I don't know, that sounds...
There must be another angular momentum in the system. It's called rotation.
rotation.
Yeah. But we'll talk about that. And it leads to some very bizarre effects. Okay? But you have to be patient for that. Okay. All right, so, well, since I have this here, you can see that, let's take this k equals 5 halves from here because it's very obvious. This is starting up this way. This is starting down. They would have crossed here. And what they do is they do that repulsion and then go off on their happy ways. Let me go to the next drawing that I was going to show. Okay, so here are a couple of, whoops. So here is the k equals 5 halves from the F7 halves orbit. Here's the k equals 5 halves from the H9 halves orbit. They're approaching each other. This is where they would have crossed, and they reflect and go like that. Okay? All right. Now you can actually estimate the wave functions. The wave function of this particle at very close to zero deformation is very close to pure F7 halves. The wave function of this particle at very small deformations is very close to H9 halves. As they go out, as the deformation increases, these two orbits will mix. Okay? And this wave function will be partly F7 halves and partly H9 halves. Other things too, but let's just talk about that. And this particle will be partly H9 halves, mostly H9 halves, and partly F7 halves. At the point of closest approach, they will be equal mixtures. After the point of closest approach, out here, this orbit, which is drawn as originating in F7 halves, actually has a wave function which is mostly H9 halves. And this one, which is drawn as if it comes from H9 halves, is actually mostly F7 halves. You can always tell what the dominant amplitude is just by extrapolating. If I put a ruler, a scale, on here and just draw back a straight line, it goes back to there. And this one goes back to there. So you can always tell. So you can actually use this to estimate the wave functions in the Nielsen scheme. And here I give a couple of examples. Can you see these numbers? Yes? No? Who said that? Yeah, but you're up in the front. What about in the back? Can you see these numbers? Okay, way back there. Okay, good. Okay, so let's look at a couple of orbits. This orbit has this name, 5 has 523. I'll explain these quantum numbers in a minute. And this one has 5 has 512. So those two orbits are this one and this one, okay? And here are their wave functions. Their wave functions look like this. They are a sum over the individual spherical single particle energies from the independent particle model times a coefficient Cj, which is a mixing amplitude. And these are always called the Cj coefficients. And this table shows those wave functions. This is J, so that's this little j, the J of the single particle orbit. And so 1 half, 3 halves, 5 halves, up to 11 halves. And this is the wave function of this orbit. So a particle in this orbit, 5 has 523, has a small amplitude for J equals 5 halves, has a bigger amplitude for 7 halves, and dominant amplitude is 9 halves, small amplitude for 11 halves. Just in case you can't read, this is 0.472 and 0.826. So it's dominantly 9 halves, and it has a large 7 halves component. That orbit is this one. So for small deformation, it would have been a dominant 7 halves component. After this avoided crossing, its wave function is dominantly H9 halves, and so you see 0.826, 0.472. So if I looked at a region of the Nielsen diagram that we haven't discussed here, you could actually go and pick off some deformation and look at where these orbits came from and whether they've had a reflection, and you can actually estimate the main components of the wave function. So it's really remarkable. You can almost write down guesses of the main components of the wave function by inspection. You can't get the signs that way. At least I can't. Okay, let's look at its so-called partner orbit. 5 has 512. This is this one. And so for small deformation, it would be mostly H9 halves. When we come out here, this arrow says where this table is calculated. Okay? It's going to be mostly F7 halves. The next important component will be H9 halves. And you see 0.836 and 0.515. Notice these are almost the orthogonal combinations. 0.47, 0.82, 0.83, 0.51. So what you're seeing here is dominantly two-state mixing with some little wrinkles. Okay? Yes?
Do you mind giving us a physical interpretation to the fact that two levels of the same K cannot cross?
Two levels that mix can never cross.
Yeah, but that's what we have seen, but it's a more mathematical interpretation.
A mathematical
From
interpretation.
my point of view, we just did it on the, we just mixed and see that they cannot never cross. But what does it mean?
I'm probably going to give too simple an answer. If you have two states that mix, they repel each other. And so as they approach closer and closer, they repel more and more. And if they repel, they can't cross. It seems too simple. By the way, this gets interesting if you talk about unbound levels. But it's still true that they repel. Is that? Okay. It wasn't very mathematical. It was just sort of. Okay. All right. Let's do another one. Was there another hand up? Yes.
I wonder how they draw this diagram.
I'm
Because for different deformation point, it depends how you connect the curve. It will be cross if you connect it by different way.
Okay, if you actually want to draw this diagram, what you do is a series of calculations as a function of deformation, and you look how the wave function of each level slowly evolves, and you can connect them very easily.
So I mean, if after the interaction,
Yeah?
the main component is changed, but if we just according to the main component, they will be cross, no.
You mean if you just did a calculation here and no other deformation, you might not be able to connect it so easily there. Is that answering your question? I don't think so. Ask it again.
I mean, in the region, the interaction.
Here?
In the interaction region. So if we, for different, with the change of information, we connect them according to the main component. So if we do this way, near cross, no deflect.
Yeah, if you want to connect by the main component, you would draw this like this. And you would draw this like this. But physically, two states that mix can't cross. And so we always draw them this way. Remember, this diagram is a sum of an infinite number of diagrams, each calculated for a given deformation. So the way of drawing it like this is sort of for our convenience. What you have at each given deformation is a wave function. And so this is a little bit of a pictorial way for our convenience. Okay? All right. I want to do another one. There are these two in blue, which are, see the color coding, 7 has 503 and 7 has 514. Remember, I'll explain these numbers soon. So the 7 has 503, 7 has 514 is this orbit. So for small deformation, it's largely F7 halves. And then it has a avoided crossing with a particle in the H9 halves k equals 7 halves. And so out here, which is where this table is for, this wave function will be dominantly H9 halves. This wave function will be dominantly F7 halves. And so if we look, here's 7 has 514. Its wave function is 0.3 for j equals 7 halves, 0.9 for j equals 9 halves. That's this orbit, okay? So it's dominantly H9 halves, even though we draw it as starting from H7 halves. The partner orbit is almost exactly the orthogonal combination. So here's 0.323, 0.938, here's 0.937, 0.336. So it's almost pure two-state mixing, and any other amplitudes are 0.09, 0.128, very small. Okay? So you can actually estimate the Nielsen wave functions by hand just simply by looking at the diagram. Yes?
So we can use this diagram, the energy and the deformation, and then go and say, okay, I have that energy and that deformation, and then I choose those lines. Okay, so this should be the orbit. Can we use it to calculate?
I think so, if I understood your question.
Yeah, well, like we get some energy, like 6.3.
Yeah.
Or some, no, 6.2, and then the deformation is like 0.5 or.
Well,
something
say
like that.
0.22 or so, yeah.
Can we assign that one to? We said, okay, so this is the quantum number that it should have.
These are the quantum numbers of these Nielsen orbits, which I'll explain in a moment. And in fact, there it is. Whoops. There we go. These are the quantum numbers we assign to the Nielsen orbits. This is what I call their parent state. In a sense, the diagram is misleading. What you just want to have are the wave functions for each orbit at each deformation. But if we do a series of calculations and trace it out and see how the wave function smoothly evolves, this is the way you would draw the lines. Okay. I want to come back to another question, which was it yours about the double curvatures? I think so. So this one, you'll notice first curves one way and then it curves the other. And what you're seeing there is, so first this level is mixing, this is the k equals a half orbit from p3 halves, and it's mixing with the f5 halves here, and so they repel each other, and so that gives you this convex behavior. And then as you go out here, this one is starting to mix with one of these others, I don't remember which one, and so it curves the other way. So you have a sequence of two-state mixings, and that gives you this sort of complicated thing. And so if you look at this orbit, which is 1/2 521, you would immediately expect that its wave function is going to be more complicated. It's not just going to be two major components, because you've got this avoided crossing and then another one here. And if you look at it, 1/2 521, it's got a wave function which is just spread out over all of these j's. 0.5, 0.35, 0.47, 0.43, 0.44, and a small one there. Okay? So just by looking at the diagram, you can actually estimate the wave functions. Now let me make a comment about the phases. As I said, you can't estimate the signs. And if you look at different Nielsen model tables, diagrams, wave functions, you'll see different sign conventions. And I don't mean simply multiplying all of them by -1. You will see things where, these two, which have opposite signs here, might have the same sign, and then these might have opposite signs. There are different phase conventions in the literature, and in most cases it doesn't matter too much, but if you take these Nielsen wave functions and then put them into some code, for example, that calculates transfer reaction cross sections, you have to make sure that code is using the same phase convention. So you can get in trouble. Okay. Yes?
Sorry if I didn't understand. How did you get the numbers in that table?
In the table? How did I get them?
Yes.
I used a code, a Nielsen code, to calculate them. And this afternoon, in the exercises, that's the first thing you'll do. We have the code. It's on your server area, whatever you call it. And you're going to actually calculate it yourself. Okay? And then you'll change some parameters and see how the predictions change after you've predicted them by hand. Okay?
Do you have an idea? Is it by doing matrices?
Yeah, what you do is you take the Hamiltonian, which I'll show in a little while, the formal Hamiltonian, which is an oscillator plus a P2 cosine theta, Y20, and that matrix element mixes the single particle states, and then you just diagonalize. Okay? All right, everybody comfortable with this? Everybody feel they understand it? I don't think it's complicated. Yes?
Well, I still don't get when they are like crossing, like you see about 126, one of them comes really down,
Yeah, okay.
the other one goes
Yeah.
up, and then they cross that.
Okay, these can cross because they have different principal quantum numbers, different oscillator shells. So they can't mix.
Cannot, but if they have the energy of 6.4 and that deformation, well, so we cannot just decide, okay, so it should be that one or this one. That's my question. So we cannot just mix them all?
Maybe you're asking if we have for certain energy, when do I, because usually we are used to filling the particles, so we have some boxes and we fill the particles, and at some point we have crossing of the boxes, and we might wonder in which box should we put the particles. So
Okay,
that energy,
we
at
will.
which level should we put the particles?
We will see very soon. We'll see very soon, and I think it'll be clear when we do it. We'll see how to do this for a specific nucleus, how to use the model, how to know what orbits the particles are in.
Let's suppose that we are like on the region of 0.3 and 6.4. We want to add some two particles, so occupy some single particle orbit. So how do we know that we are going into the the right side on the diagram.
Okay, so that's a good question. So let me phrase the question my way and see if I'm understanding your question. So suppose we have a nucleus, let's say here, okay, where the last two particles are in this orbit. And now I go to a nucleus which has two more neutrons. Okay, how do I know whether to put those two neutrons in this orbit or maybe in some other orbit because the deformation has changed, right? Okay, we will see that. Okay, you have, in order to use the diagram, you have to know the deformation. And first of all, the deformation changes slowly, but we will see how to do that. Okay?
Because generally evolution should come from this 82 somehow curved.
Yeah, exactly.
126,
Yeah. In general, if you start with a closed shell, the deformation here will be 0 as you start to fill nucleons. Think of the P factor. Deformation will come out, and it'll maximize somewhere here, and then at the end it'll curve back. And we'll see how to do that. Okay? So after I introduce the model, we're going to do practical calculations. Okay? Okie dokie? All right. So think about what we've done. We've deduced, okay, you might want to put that in quotation marks, the Nielsen diagram without calculation, just thinking about the shape. And you can now do this for any shape. You can do it for an oblate shape, which is what you asked about, Vasil, or you can do it for a hexadecabole shape that looks roughly like this. Now, this is the only little, what do you call these things that you get off the web? I pulled this shape off of PowerPoint. And so the nuclei don't come to points here. Just realize that it's supposed to be rounded, okay? So you can actually calculate a Nielsen diagram for this. And in fact, you'll do that this afternoon. And you'll do it two ways. You'll do it by hand, just by thinking about it, and then you'll calculate it and see if you were right. Okay? All right. What happened? Why did that disappear? Okay. All right, the quantum numbers. Those quantum numbers you saw, let me go back. Okay. They always have a bracket. You probably can't see this, with 3 numbers inside the bracket and a half integer number out to the left. Okay, and here's what those numbers are. So those numbers are k, pi, n, nz, and lambda. Okay. Now, k you know. That's the projection of the particle on the symmetry axis. Should be called omega, but we tend to use k. Pi is just the parity. Now, let me come back. Parity is an important idea. So in the 82 to 126 shell, as you know, most of the orbits have negative parity. F7 halves, H9 halves, P3 halves, F5 halves, P a half. There's one orbit with the opposite parity, I13 halves. Okay? That's positive parity. It has a name. It's often called the UPO, unique particle orbit. And because it's the only orbit in this shell with that parity. Now, somebody asked, why are some of these orbits curved, which we've discussed, and why are some straight? So these are almost purely straight. Now you can answer that, right? Why are those orbits straight? Exactly. Is that what you were going to say, whoever was over here? Okay. There's nothing else that can mix with it. Now, that's not quite true. It, in principle, could mix with orbits from this shell, which has the same oscillator shell, but that's pretty far away, and so the mixing is very small. And you will see that this afternoon. Okay? So, okay. So, k is the k value, pi is the parity. N is the principal quantum number, the oscillator shell, and going back, this is oscillator shell n equals 5. If you just count up from the bottom, you'll see that. And so the first quantum number in brackets for all of these orbits, except the I13 halves, is going to be a 5. The I13 halves comes from the next shell up. It comes down because, comes down because of the spin orbit force. So it really is from oscillator shell 6. And so that one will have a 6 here. Yes?
So you explained how we know which K projections are going to go up and down and so on. But how do we know because these levels are crossing a lot. So it seems like the splitting in this K value is large compared to our original shell value.
Yes. Yeah.
So how do we get a grasp for why this is so large?
Okay, so the mixing depends on two things, as you know, the energy separation and the matrix element. The energy separation, that's clear. You can see that here. The matrix element are the matrix elements of Y20 between single particle orbits, and that depends on which single particle orbits you have. Generally speaking, if you have two orbits differing by 2 units in orbital angular momentum, okay, they will tend to mix more. And if you have things like F7 halves, P a half, oh, that one actually will, but it's so far apart, but H9 has P a half will not mix very much. So the quadrupole interaction will mix orbits differing in L by 2.
But even without mixing, like this, these I values that are completely straight,
Yeah.
the bottom one is going to go down almost by an entire unit of energy.
Oh, you're saying the effects are big.
Yeah.
Oh, they're huge. Yeah, they're huge. And you'll calculate them this afternoon. It depends on the strengths. It depends on the orbits of particles in a deformed nucleus. But yeah, they're big effects. Okay, so the second quantum number is in many ways the most important. It's NZ. So it's the number of nodes in the wave function on the z-axis, the symmetry axis. And so you can think of it this way. The larger NZ is, the more the wave function is extended in the z direction, in the direction of the axis of symmetry. Okay? And if you remember, a particle going around the nucleus, around the equator, around the axis of symmetry, is closer to the nuclear matter. Its energy will be lower. So the lowest line levels will have the highest values of n sub z. Okay. Lambda is not so important in practice except for one aspect when it comes to Coriolis mixing. It's the projection of the orbital angular momentum on the z-axis. Sigma, which I don't write up here, is the projection of the z component of the orbital angular momentum on the z-axis. And K is the sum of the projection of the orbital angular momentum and the spin angular momentum on the z-axis. So K is always lambda plus or minus a half. And if you specify lambda and K, it's redundant to specify sigma, so usually it's not set. Okay, one other thing, n sub z plus lambda has to be even or odd according as n is even or odd. So how do you assign these quantum numbers to these orbits? The basic idea is that the more the particle is going in an equatorial plane, the more it's aligned with the nucleus, the larger n sub z is going to be. Okay? And there are two ways of doing it. Well, we'll talk about them. So the lowest orbit is most aligned with the bulk of the nucleus. It's most extended in the z direction, so it has the largest n sub z and the smallest k. Knowing that, we can assign these quantum numbers to any orbit we want. Okay, and so I'm going to do that now. I'm going to do it two different ways. So I blew up the 82 to 126 section and also the 50 to 82 because the H11, this is mostly n equals 5, right? Oscillator shell 5, F7 halves, H9 halves, P3 has, F5 has, P a half. But because of the spin orbit force in the shell model, the H11 halves is also a member of that oscillator shell, and it's going down to the next shell below. So if we want to assign all the quantum numbers to the n equals 5 orbits, we need to include this. Okay, so there are two ways of doing this. I'll do both of them. These dots just simply help you see the orbits. The fact that they're moving around in deformation means absolutely nothing. It just means I didn't have room to put them over here. It's just, okay, so that means nothing. Okay, so the lowest of all the orbits from the n equals 5 shell is going to be the k equals a half orbit, okay, from the H11 halves, because spherical single particle energy is lower. And that will have k equals a half, so if you can't read this, it says 1/2. And then in the brackets, there are three quantum numbers. N equals 5, all of these will be n equals 5. N sub z is 5. It's the most extended in the z direction. And if you remember, n sub z plus lambda has to equal n, so n sub z is 5, big N is 5, so lambda must be 0. So you have 1/2 5, 5, 0. Okay? Now we go to the next orbit. That's going to be a k equals 3/2 orbit. Okay? It will be a little less extended in the z direction. The k, the orbital angular momentum is tilted a little. And so that will be 3/2, 5, 4, 1. So I've reduced n sub z by 1 from 5 to 4. And to make n sub z plus lambda equals 5, I have lambda equals 1. Is that clear? So the next one, pretty obvious, I think, will be 5/2. So 1/2, 3/2, 5/2, 5, 3, 2. The only thing that's changing is the number of z quanta, because the orbit is gradually tilting with respect to the nucleus from being equatorial to polar. Yep.
So why this NZ plus lambda is going to be the total quantum number?
Because I don't know. I don't remember. Do you know off the top of your head? Why nz plus lambda has to equal capital N? I'll find that out. I've forgotten. Good question. Okay. Okay, so the next one is 5/2, 5, 3, 2. So what will the next one be? So we've had 1/2, 5, 5, 0, 3/2, 5, 4, 1, 5/2, where is it? 5/2, 5, 3, 2. Next one will be? He said 7/2, 5, 2, 3. Does anybody agree with him? Anybody disagree? Does everybody see where he got that from? We need a coffee break, I think. Okay, so we started off, we're talking about the n equals 5 oscillator shell. So the first quantum number in the brackets is always going to be 5 for these orbits. The lowest energy orbit will be k equals 1/2. So it'll be going around the nucleus this way. And it will have the largest value of n sub z, the most extension in the z direction. And so that's going to be 1/2, 5, 5, 0. As we now go with orbits that are tilted more and more and more to the z-axis, the k value will increase, 1/2, 3/2, 5/2, 7/2, and so on. The n sub z value will decrease, and so you will have 1/2, 5, 5, 0, 3/2, 5, 4, 1, 5/2, 5, 3, 2, 7/2, 5, 2, 3, as you said. What's the next one? Aha! You can't see it there. 9/5, 5, 1, 4. Very good. And the last one? 11/5, 5, 0, 5. Everybody see how he got that? Okay. Now let's go to the next orbit. So f7/2. The lowest orbit is going to be k equals 1/2. And it's going to have the largest possible extension in the z direction, except it's higher in energy than this. This has 5, 5, 0, so this has to be 5, 4, 1. You just reduce n sub z by 1. And now you can do the others very easily. This is 5, 4, 1. 3/2, 5, 3, 2. 5, where is it? No, sorry. So 1/2, 5, 4, 1. 3/2, 5, 3, 2. 5/2, 5, 2, 3. And 7/2, 5, 1, 4. Now we go to the next orbit, h9/2. And you have 1/2, 5, 3, 0. I've reduced n sub z by 1. The next orbit will be 3/2, 5, 2, 1. 5/2, 5, 1, 2. 7/2, 5, 0, 3. And I can't go any lower, so it's going to be 9/2, 5, 0, 5. Yes?
So here it is not nz plus lambda is equal to total number of quantum number.
Yeah, I just saw that. And you know, that's a very good point. I said something completely wrong before. I said that n sub z plus lambda has to equal capital N.
Only for the high j.
Only for the high j. Okay. Okay, so do you see how this works? Is everybody totally confused, or they get it? Okay, there's another way of doing it, and at the risk of confusing you a little more, I'll say what that is. What we did here is we started with all the various orbits from a given single particle state, and we assigned their quantum numbers. And then we went to the next single particle state and assigned their quantum numbers, and then the next. What we could do alternately is take all the orbits with k equals a half. Okay, maybe that's easier. So the lowest one is going to be 1 half 550. The next k equals a half will be 1 half 541. The next k equals a half will be 1 half 530. The next k equals a half will be 1 half 521. The next one will be 1 half 510. And the last one will be 1 half 501. So maybe that's easier. You take a given k and you just sequentially reduce n sub z. Yes?
But what about the last quantum number? Sometimes it's 0 and sometimes it's 1.
Yeah, the sum of the two n sub z and lambda has to have the same parity as the principal quantum number n.
Okay.
So it's either odd or even. Okay. Is that clear? All right. Why don't we, well, what comes next? No, that's how do we use the model. So I know it's only 10:20, that's 10:26, that's close enough. Why don't we stop here? When we come back, I'll quickly go through this again in case you're confused, or maybe I'll ask you to go through it. But just let me ask, do you think you get this? Do you get the labeling? Okay. Now, let me make a comment about the computer code. The computer code will calculate the wave functions and the energy levels of all of these Nielsen orbits for any deformation you tell it. The computer program, though, is dumb. It doesn't know the Nielsen quantum numbers. So you're actually going to have to look at the wave functions and the energies and assign the Nielsen quantum numbers. And that will give you some experience with this. And it sounds painful, but it really is pretty simple. Okay, all right, let's take a break.